Suppose we have some function like f of x equals, I don't know, x to the fourth minus 7x cubed plus 8x squared minus 3x plus 1 times x to the sixth minus 3x to the fifth plus x to the fourth. Hold on 1 second. Okay, sorry about that. Plus x to the fourth, I don't know, what do you want? Minus x to the second plus 10x, something like that. Right? Two really sort of gross polynomial functions being multiplied together. Aren't those lovely? Don't you like those? Aren't they great?
No.
No, yeah, I don't like them either. Could we find the derivative of this?
Sure.
Sure, I like that answer. Yeah, the answer is yes. The only method that we have right now, before I teach you this rule we're about to learn, to find this derivative is to go through and distribute all of this crap out. And distribute all of these things through here and getting a long polynomial with a bunch of terms that I have to combine together and then using the power rule. And that seems pretty unpleasant, right? I mean, I have 5 different terms here times 5 different terms here, which means I'm going to have 25 different terms as I write it out and have to combine the like terms and then take the derivative, right? Looks like a pain, true?
Yes.
Would you agree? Yes. Okay. Unfortunately, it would be really cool if I could just take the derivative of this function and the derivative of this function and multiply them together, but that does not give you the correct derivative. I'm going to demonstrate that really quickly with something nice and simple. Like suppose we had x squared minus 1 times x plus 1. This is not so bad to distribute together, right? If I distribute this together, I get x cubed, right? And then plus x squared, and then minus x and minus 1. Would you all agree with that? No. If I distribute that through?
Yeah.
Okay. And then if you were to take the derivative of that using the power rule, you should get 3x squared plus 2x minus 1. Everybody agree there?
Yeah.
All right. So if we were to try to use that other method where we said, well, take the derivative of x squared minus 1. What's the derivative of x squared minus 1? What's the derivative of x squared minus 1?
2x.
2x. And what's the derivative of x plus 1?
1.
1. Is 2x times 1 the same as this?
No.
No, this is very bad. We cannot do this, right? This does not work. We have to have this other rule. This other rule that we're going to develop in just a second here is called the product rule. And it will allow us, without doing any distributing, to find the derivative that should still come out to be the same as if we were to distribute it out and then use the power rule. Sound good?
Yes. Yep.
Right, cool. So here it is. This is the product rule. The product rule says if I have two functions being multiplied together, u times v, then their derivative should be u times the derivative of v plus v times the derivative of u. Good? That's the rule. We're going to prove the rule right now. This rule you will need to memorize and know forever from now until the end of your life. Sound good?
Yeah.
All right, cool. So let's prove it. If I were to try to find the derivative of something that I don't know how to find the derivative of, the way we've been doing those is by using a difference quotient, right? We write out the limit as h approaches 0 of u of x plus h v of x plus h minus u of x v of x all over h. Okay, would you agree that this is the difference quotient for two functions multiplied together, u times v?
Yeah.
All right, cool. So what we're going to then do is we're going to just introduce some new terms in here because as it sits, this limit is not one that we can deal with. And you don't need to know how or why we chose these, just some smart person figured this out a long time ago. These are the terms that you need to plug in here. So we're going to add in a u of x plus h times v of x, and we're going to subtract a u of x plus h v of x in the numerator of this. So I'm going to have u of x plus h v of x plus h minus u of x v of x, and then plus u of x plus h v of x, and then minus u of x plus h v of x, all over h. So effectively, I've done nothing, right? I've added in some term and I've subtracted that same term, which should come out to just cancel each other out. True?
True.
So we've not really affected this in any way, other than we've added some extra terms that we can play around with to do some factoring and deal with stuff. So what we need to do then is we need to find a way to break this limit up into two different limits so that we are able to evaluate some of them. So we need to choose a couple of the terms in this numerator to put together, and then another two of those terms in the numerator to put together and see if we can somehow simplify them down. So anybody have any idea on which one they want to combine with this term? This u of x plus h v of x plus h?
We can subtract the last two terms, so u times x plus h, v times x minus, yeah, so those last two terms right there.
These ones?
Yeah, we can subtract those.
What do you mean subtract them?
Well, we can cancel them because it's just the same thing.
Right, we could cancel them out. I mean, but if we cancel them out, we're back to where we started, right? And we'd added these things, we'd added those things in to see if we could use them
Oh, okay.
to do something. So let's take one of these two terms and put it with this term. Anybody have an opinion on which one, the third one or the fourth one?
The fourth one.
The fourth one? Okay, let's just give that a shot and see what happens. That's going to leave me with what here? It's going to leave me with the other two terms. The limit as h approaches 0 of u of x plus h v of x and minus u of x v of x up there, all over h. Do you guys agree with that or no?
Yeah.
Okay, cool. So what do the terms in the numerator of our first limit have in common?
They have the u of x plus h.
All right, they both have a u of x plus h. So could I factor that u of x plus h out?
Yes.
All right, so let's do that. The limit as h approaches 0 of u of x plus h. And what's left if I factor that out? I think I should have a v of x plus h minus v of x. And then all of this is over h, correct?
Yes.
All right. And then I also have a plus, and then this other limit, they had something in common. What did they have in common?
A v of
They-
m.
Yeah, v of x. So we'll say the limit as h approaches 0 v of x, and what's left? U of x plus h minus u of x, and it's all over h. And with any luck, we will notice that what is occurring within our limits.
It's a constant times the difference quotient.
Yeah, it's not quite a constant, but it's some function here times the difference quotient. This right here is the difference quotient, right? And this right here is a difference quotient. True? So what we can do, this is because this isn't a constant, because it does have an x in it, and it's got this h, which is our variable in it. We have to just separate this out as its own limit. So I could say the limit as h approaches 0 of u of x plus h times the limit as h approaches 0 of v of x plus h minus v of x all over h. And how come I didn't put an over h on this one?
It's already in the other one.
Yeah, we put it in this one. If I put one here, as I multiply these together, that would make an h squared. I would have had to have had an h squared up there, but I don't, right? So I could have applied the over h to either one. I chose to apply it to this one because then that makes this one look like the difference quotient. So let's look at the other side. I can do a very similar thing, right? This one's going to be v of x, and a limit as h approaches 0 of, this one is u of x plus h minus u of x all over h. Everybody good with that or no?
Good.
Cool. So from there, as h goes towards 0, what does u of x plus h become? What's this very first limit in the brackets become?
U of x.
Should just become u of x, right? And what about this one here? This is the limit as h approaches 0 of the difference quotient for what function?
For v of x.
For v of x. And what's the limit as h approaches 0 of the difference quotient of v? That just represents the derivative of v, doesn't it? That is the definition of the derivative. Everybody good with that becoming the derivative of v, dv dx?
Yes.
Okay. And then what about this? As h goes to 0, v of x is, well, still just v of x. And as h goes to 0, u of x plus h minus u of x over h, that's the difference quotient of u. And so that's just the derivative of u. And this right here is exactly what I had on the previous page for the product rule. So this tells me that anytime I want to find the derivative of a product of two functions, I can use the first function times the derivative of the second, plus the second times the derivative of the first. Any questions on that process? How we got there? Any of that fun stuff? Everybody good? All right, let's see if we can do this with a function like this. X cubed plus 1 times x squared plus 3. So this function here, u, is being multiplied by this function here, v. So one method we can use to find this derivative is the product rule. And the product rule should tell us that f prime of x equals, what's the product rule? It is the first function, u, which is x cubed plus 1, times the derivative of the second function, which is what's the derivative?
X.
Just 2x, right? Plus the second function, v, times the derivative of u, which is
3x squared.
3x squared. And if I wanted to simplify this out, I could. This would be 2x to the 4th plus 2x plus 3x to the 4th plus 9x squared, which would give us 5x to the fourth plus 9x squared plus 2x. Good or no?
Good.
All right, now real quickly here, let's show that this is correct. We could distribute this out before we took the derivative to get f of x equals x to the fifth, right? X cubed times x squared, and then 3x cubed, and then x squared, and then 3. You guys agree with that distributing?
Yeah.
And what would f prime of x then be? Well, the derivative of x to the fifth is 5x to the fourth. The derivative of 3x cubed should be 9x squared, and the derivative of x squared should be 2x, which is exactly what we got using the product rule. Agreed?
Yeah.
Yeah, that was pretty nice, huh? Now, I would say distributing it out and taking the derivative is probably a little bit easier, wouldn't you? Probably a little bit easier, maybe not a lot
I
easier.
feel like this is a trick question.
No, I mean, I think this is easier, personally. But the product rule becomes very important, especially when we don't just have simple polynomials in here. Because suppose I ask you to take the derivative of, sine x times cosine x. Well, that's one function times another function, right? But there's no way to distribute this together. Is there?
Not really, no.
Not really, no. So it's very important that we are able to use this product. So we're going to use it on some simple functions like these nice polynomial ones where we can check our work and make sure we did it right and get used to the rule before we throw in all these extra rules that are going to complicate things a little bit more. Sound good?
Yep.
Cool. So let's real quickly do another one. You guys want to do this one on your own real fast?
Yes.
Yeah.
All right, I'll give you like 2 minutes. Use the product rule. You don't need to check it by doing the distributing. Just use the product rule and find the derivative. So we had u and we had v, and so f prime of x ought to be u times the derivative of v, which is 2x plus 3, and then plus v times the derivative of u, 3x squared. Is that what you all did with your first step there?
Yes.
Yeah.
Cool. And if this was the AP test and this was a free response, that answer would be perfectly fine. But multiple choice, they're probably not going to leave it like that. They'll want you to distribute it through. So just to make sure we can successfully do that, that should be what? 2x to the fourth plus 3x cubed plus 4x plus 6 plus 3x to the fourth plus 9x squared minus 3x. I'm sorry, 9x cubed minus 3x squared.
Yeah.
So 5x to the fourth plus 12x cubed minus 3x squared plus 4x plus 6. Hopefully I did my distributing right.
Yeah.
I did? Oh, good. All right, perfect. Any issues with that?
Looks good.
All right. Let's do one more of these. And then we're going to not just find the derivative, but also figure out when it has horizontal and vertical tangent lines. So you guys want to work on finding the derivative on your own, and then we'll deal with the rest of it together?
That
Yeah.
sounds good.
All right, cool. All right. I give you 1 or 2 minutes to find the derivative, and then we'll deal with it. Ready, go. Make sure you got your derivative right first, and then we'll worry about this vertical and horizontal tangent line stuff in a second. So using the product rule, this should become f prime of x is u, x to the 1/3, times the derivative of v, 2x minus 3, plus, and then derivative of x to the 1/3 should be 1/3 x to the negative 2/3, and then times x squared minus 3x plus 2. That's what you got for your basic derivative.
Yeah.
All right, cool. So now we want to know, when does this function have horizontal or vertical tangent lines? Well, we've talked about horizontal tangent lines. That's when the derivative is equal to
0.
0. But vertical tangent lines would be when the derivative is, what do you think?
Maybe like infinity?
Yeah, infinity, or in fact, we'll just say anytime it's undefined, we could have a vertical tangent line, right? If the derivative is at infinity, that's sort of like going towards an undefined value, right? And we know that vertical lines have a slope that is undefined, and so if that slope, the derivative, is undefined, it should be a vertical tangent line. So looking at this, can you tell me all values of x that make this equal to 0 and make it undefined? Just by looking at this in this form? Probably not, right? That's a little bit of an issue. So we need to work on some of our algebra skills probably to make sure that we can convert this into a form that makes it easy to see if this derivative is 0 or if this derivative is undefined. So I'm gonna quickly ask you this question. Anybody know how we should be going about this? How can we simplify this down or rewrite this to help us figure out when it's equal to 0 or when it's undefined? All right, I'll take that as a no. So I'm going to ask you this question. If I asked you, when does this equal 0? What would you do? Besides just tell me like what the values are because you're okay at arithmetic. How would you algebraically solve this?
You could factor out x squared, right?
Right, factor out x squared, you get x squared times x plus 1 equals 0, and you'd say, ah, cool, 0 product property, right? X squared is 0, that's 0. X plus 1 is 0, that's -1. We'd have our two answers, right? Yeah? This
Yeah.
allows us to use the 0 product property because now it's a term times some other term that I can set equal to 0, but I don't have that up here. I've got a term times another term plus a term times another term, which complicates things. This plus sign in the middle makes for an issue. So if I could find a common term to factor out of all of this crap up here, that might help us out. So when we did x cubed plus x squared just now, what did we factor out?
X squared.
Factored out the x squared, which was the smallest of the powers on x. So let's try that up here. What's the smallest of all the powers on x up here in our derivative?
-2/3.
Yeah, x to the -2/3. So let's factor out x to the -2/3. So if I take x to the -2/3 out of this whole term right here, what's left from the x to the 1/3?
Is it just x?
It is exactly that, just x, and then I still have a 2x minus 3. And we can check to make sure we've done this factoring out correctly, because if we distribute x to the -2/3 to this term, we should get what was up here. And x to the -2/3 times x to the first is x to the 1/3 and then times 2x minus 3. So that should be exactly as it is. And what's left from all this stuff at the end here, this term? If I take an x to the negative 2/3 out of 1/3 x to the negative 2/3, that should be
1/3.
1/3, and then we still have all of this x squared minus 3x plus 2. And if I were to distribute the x to the negative 2/3 back to this half of it, I should get this exact same thing that I had up there before. True?
Yes.
All right. So, well, let's see if we can simplify what's in there. The x to the negative 2/3 can drop to the denominator, right? Since it's a negative 2/3, and it can become a positive 2/3 down there. And x times 2x minus 3 is 2x squared minus 3x. And this is plus 1/3 x squared, and then minus x, and then plus 2/3. Good or no?
Good.
All right. I don't like having little fractions up here. How many of you like having little fractions up there? None of you? Good. So if I were to get a common denominator of 3 for all of these terms, could I drop the 3 in each of these denominators to my actual denominator? This one would become a 6x squared. This one would become a minus 9x. This one already has the denominator of 3, so that'll just stay as an x squared. This one will become a minus 3x, and that one already has the denominator, so it'll become a plus 2. Everybody good with that or no?
Good.
All right. So our final derivative then, if we simplify that numerator, is 7x squared minus 12x, I think, right? Plus 2 over 3x to the 2/3. And now this is in a much easier form for us to figure out when it equals 0 and when it's undefined. So let's do the undefined part first. That's actually the easier part. When is a fraction undefined?
When the denominator is 0.
When the denominator is 0. So f prime is undefined if 3x to the 2/3 equals 0. Well, what x value makes that true?
Zero.
0. And when does f prime equal 0? When does a fraction equal 0? If its numerator equals 0, right? True?
True.
Okay. So when does this equal 0? Well, unfortunately, that doesn't factor, so we'll use the quadratic formula. That'll be x equals 12 plus or minus radical 144 minus, what is that? 2 times 4 times 7, that's 56, all over 14. Let's see, 144 minus 56 is 88, right? And 88, if I simplify that, ought to be 2 root 22. Hopefully. And we can divide everything in there by a 2. So we get x equals 6 plus or minus root 22 over 7. So what we've found out here is that when x is 0, our function should have a vertical tangent line. And when x equals those two values, our function should have a horizontal tangent line. And that tells us actually a pretty large amount about what this function is doing and how it behaves during its domain. So let's quickly graph our original function in Desmos. what was our original function? X to the 1/3, right? Times, what was it? X squared plus 2x minus 3 or something? I don't know.
It was x
Yeah.
squared minus 3x plus 2.
Minus 3x plus 2. I knew there was a plus and a minus and a 2 and a 3. I just couldn't remember what they were. So this was our function. And if we look at x equals 0, let's zoom in just a bit. At x equals 0, well, yeah, it sure does look like it has a vertical tangent line there, doesn't it? Looks like it's come up to be almost perfectly vertical there. True?
True.
And then here is 0.187 where it should have a horizontal tangent line. And here is 1.527 where it should have a horizontal tangent line. And those values were supposed to be 6 plus the square root of 22, right? Divided by 7, 1.527, that's exactly what we got there. And if we change it to a minus 0.187, which is what we got there. Isn't that cool?
Yes.
All right. At least one person thinks that's cool. I think it's pretty neat. We're going to spend a lot of time as we move forward into the applications of derivatives, talking about when things have horizontal and vertical tangent lines and what that means. And we're going to be able to, within the next couple of weeks here, take pretty much any function I give you and draw almost a perfect graph of it just by using calculus and derivatives and second derivatives and all that stuff to model the function's behavior. It's going to be really exciting. Any questions on that?
So the horizontal tangent lines are when it changes from increasing to decreasing or the other way around. And then the vertical tangent lines are just when the function kind of like looks like a vertical line sort of at that point or approaches vertical.
Yep, that's exactly right. Yep. And we're going to talk as we go through it, we're going to actually talk a lot more about that when we get into the applications. And I'm going to, we're just kind of scratching the surface right now, learning these rules for taking derivatives. But as we go through, I want you to at least kind of have a general idea of what's going on, so that when we have learned all of the rules, and there's, believe me, plenty of rules. We're going to spend most of next week learning all the rules: product rule, quotient rule. There's something called the chain rule, something called the inverse rule. We have to learn derivatives of the trig functions, derivatives of exponential functions, derivatives of logarithmic functions, derivatives of inverse trig functions, all this junk. And once we learn all those derivatives, we're going to be able to apply all of this knowledge that we've gained into perfectly graphing functions and looking at some real world applications of what these derivatives do for us, rather than just sort of in a sort of pure math sense also. But yeah, for right now, yes, that's what the horizontal tangent lines mean and what the vertical tangent lines mean. But there's so much more to it. It's going to be great. You all think I'm crazy now, but that's okay. You're probably right. All right. Should we move forward?
Yes.
Okay. Anybody else have any more questions? No? Okay. We are going to talk about the quotient rule, and the quotient rule is proven very, very, very similarly to the product rule. Now, I'm not going to go through and prove it. If you really want to see me go through and prove it, we're a little bit running behind here. I proved it during fourth period today because I didn't get the memo on this AP test stuff that I had to deal with for you guys. So they had an extra 15 minutes and we proved it. If you want to see how to prove the quotient rule, you can go watch the lecture from fourth period today once I get it up on YouTube. But it's basically the same. What you do is you get a common denominator here for these, and then once you've got the common denominator, you add in a u of x, v of x, and you subtract a u of x, that's not an x, a u of x, v of x term into it, and you do a very, very similar process to what we did with the product rule. So if you want to see me prove that, the 4th period lecture has it, but it's not really important to us being able to successfully use this thing called the quotient rule. So this right here is the quotient rule, and the quotient rule will allow us to find the derivative of any quotient of 2 functions. So for example, something like x squared minus 1 over x squared plus 1, where there's no other good way to do that. We can't just like, well, okay, that's a little bit of a lie. There is another good way to do it, but not as good of a way as we're going to do. Where we can't just like distribute a bunch of polynomial crap together to find the derivative, where it's a division thing, where it's, there's not some simple algebra tricks. We have to actually use this rule. So you're going to want to memorize this rule. The quotient rule says the derivative of one function divided by another is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So anytime you have a quotient of two functions, one function divided by another, you have to use this rule. If I give you this problem, and don't worry, I'll go back so you can finish writing it down if you want. If I give you this problem, you cannot say, oh, that's just 2x over 2x. You can't just take the derivative of the numerator divided by the derivative of the denominator. It does not work that way. You must use this rule. Good? Everybody okay with that? You'll use this rule anytime you have a quotient of 2 functions, drawing lots of stars around it because it's important.
So like when we did the last problem, like you didn't really like distribute for the product rule. So like, do we also not really have to distribute for this one unless it's like specified?
What do you mean I didn't distribute? Like
when you first got the derivative, like you didn't like distribute out like everything. Yeah.
Yeah, you don't need to distribute it all out. On the AP, so here's the deal. You don't need to distribute it out, especially on the AP test if it's free response. An unsimplified numeric or algebraic answer is okay. They don't have a problem with that. But the chances of them asking you for this derivative, the derivative of this in the free response, is slim to none, right? They might ask you, when does it have horizontal and vertical tangent lines? And then you need to be able to simplify it down into a usable form like we did. They could ask you, what's the derivative of this in the multiple choice? And in which case their answer might look like this, or it might look like this, or it might look like this fully simplified version that we got eventually. So you've got to be able to do it, but I'm not going to tell you you have to do it every time. So if you don't want to simplify fully, that's okay. Just know that you might need to for context in one of the problems. Does that make sense?
Yeah, thank you.
All right. So we're going to use the quotient rule to differentiate this. When I say differentiate, that just means find the derivative. Okay, so if I tell you differentiate this function, that means find the derivative of this function. And using the quotient rule, because this is u divided by v, the derivative ought to be f prime of x equals, what does the quotient rule say? It says v, so x squared plus 1, times the derivative of u, which is 2x, minus u, the numerator, times the derivative of v, the denominator, all over v squared. Good or no?
Good.
Cool. And you should simplify this down a little bit. I mean, you should be able to, because it does simplify down fairly nicely. That becomes a minus 2x cubed and a plus 2x over the x squared plus 1 squared, which gives us 4x over x squared plus 1 squared. And that's the derivative of x squared minus 1 over x squared plus 1. Easy enough with the quotient rule?
Yep.
All right. Let's take a look at the next one. You guys want to do this one on your own real quick?
Yeah.
All right, I give you 2 minutes. So use the quotient rule to simplify this down. Or to find the derivative and then simplify it a bit if you want. So f prime of x ought to equal what? Our denominator times the derivative of our numerator, which is 6x minus 1 minus our numerator times the derivative of our denominator, which is 8x, all over that denominator squared. Everybody good with that?
Yes.
And if you wanted to distribute all that out, cool, but I'm not going to bother to distribute it all out because it seems like a lot to distribute. And let's do it. What do we get? We get 24x cubed plus 30x minus 4x squared minus 5, and then minus 24x squared, and then plus, 24x cubed, and then plus 8x squared, and minus 16x. I figure we should distribute it out and make sure you all that did distribute it out got the right thing. The x cubes cancel out, right? So we got an 8x squared and a minus 4x squared, so 4x squared plus 30x and minus 16x ought to be plus 14x and just a minus 5. Is that what you all got if you distribute it out? Hope I didn't miss any terms in there.
Technically speaking, can't you use the product rule and the quotient rule interchangeably if you have a negative denominator?
If you have a negative denominator, what do you mean?
Or negative exponent in the denominator?
If you had a negative exponent in the denominator, yeah, you could. I mean, if it was just a negative exponent in the denominator, yeah.
Can you like put it to the power of -1 and then just use the product rule just for fun?
Oh, I see what you're saying. So like if you wanted to write, so to write this, you're saying is 3x squared minus x plus 2 times 4x squared plus 5 to the -1?
Yeah, exactly.
Yeah, you could, but the problem with that is finding the derivative of 4x squared plus 5 to the -1 is a little more complicated because that's just not like straight power rule issue. So we don't have a way to find that derivative yet.
Okay, I see. Thank you.
Yeah, we will have a way to find it, but we don't currently. So, all right, everybody good with that? All right, one more rule for today. It's called the reciprocal rule, and it's for finding the derivative of the reciprocal of a function, which is sort of like what we were just talking about there. 1 over a function g of x, let's say. And this is just an extension of the quotient rule. So what we're going to do is we're going to use the quotient rule to prove that the derivative of this is equal to negative g prime over g squared. So using the quotient rule, this is a function 1 divided by another function g of x. We should get the denominator g of x times the derivative of the numerator. What's the derivative of 1? 0, right? Minus the numerator times the derivative of the denominator. All divided by the denominator squared. Good or no? And what does that tell us? That tells us that the g of x times 0 is just 0, and we end up with negative g prime over g squared, which is exactly what this reciprocal rule said, right? That it should be negative g prime over g squared. So just using the quotient rule with a constant in the numerator. Suppose that was suppose it was a 2 over g of x, then this would be a 2g prime of x over g squared. If it was a 38 over g of x, we'd have a negative 38 g prime of x over g squared. Does that make sense?
Why did you use like not u and v for this one, and like you used like g of x instead?
I don't know. Just for the heck of it. I don't know. Different letters. Didn't want to discriminate. I don't know.
Okay.
Yeah, no particular reason. All right, last problem we're going to do here today. We're going to use the reciprocal rule because this is 1 over a function. So differentiating this or taking its derivative ought to give us what? Now that we know that rule, negative g prime, which is what? Or negative denominator's derivative, which is 6x squared plus 5 over the denominator squared. And that's it. That is the derivative of that using the reciprocal rule. Everybody okay with that or no?
Can you go back to the previous slide?
Sure.
Okay, thanks.
Any questions or issues with this last derivative here?